Welcome everyone to the week 2 tutorial session. I am Rati Ludhani, pursuing PhD at Department of Mathematics, IIT Bombay. Today we will discuss sample questions related to week 2 and partly from week 3. So basically we will discuss full assignment of week 2 and some sample questions of week 3. So let's begin. So this is a true false question. So let P be a poset and A and B belongs to P such that A meet B exists. So to recall, what is A join B? A join B is the greatest element of the set, or you can say subposet, where T belongs to P such that T is less than or equal to A and T is less than or equal to B. So we are just looking for kind of a GCD thing, like in numbers, that is GCD. So yeah. And just to recall, this is meet and this is join. A join B is the least element of the set T belongs to P such that A is less than or equal to T and A is less than or B is less than or equal to T. So this is kind of LCM for numbers. So what I mean by numbers, so when we take Dn poset with divisibility rule, there this is just GCD and this is LCM. Okay, so right now we are in general setting. So this is a general poset where for sum, so this is not for all A and B, this is just sum given that for sum AB belongs to P such that A meet B exists. Okay, so it has been asked, what can you say about A join A meet B? So will this exist with these many conditions? So can you conclude anything about this element? So let's see. So what is this? This is basically to write as a definition. What can you say? This is least element of the set T belongs to P such that A is less than or equal to T and A meet B is less than or equal to T. So we are searching for the least element of this set. Now what does that mean? So what can you say about this set? So two conditions are there. So T is such that A is less than or equal to T and A meet B is less than or equal to T. What do we know about A meet B and A? So we know that A meet B is the greatest element coming from where? Greatest element coming from the set T belongs to P, or if you are confused, you can use S, such that T is less than or equal to S and Now we are just with S. So S is less than or equal to A, and S is less than or equal to B. So what does that mean? Whatever this element is, this is going to be less than or equal to A. Also, this exists, so we can say that this element exists. So we have that value. So with these two things, since A meet B exists, and A join B is less than or equal to A, with these things, what can we write? Now it has been said that A is less than or equal to T, and A meet B is less than or equal to T. So that means we can combinedly write A is less than or equal to T, because if A meet B is less than or equal to T, then this implies A is less than or if A is less than or equal to T, then A meet B is going to be less than or equal to T anyway. So we can write this is the least element of this set, and that means, and this means what? Now you are searching for an element T such that A is less than or equal to T, and least element of such kind. So we can just pick A, and that will be the least possibility, because A belongs to B and A is less than or equal to A, and you cannot have something in between because these are same. So this has to be A. This I can erase that. So this is equal to A. So A join A meet B, which is A, exists. So we can say that this is a true statement. Hi Mahalakshmi.
Good evening, ma'am.
Good evening. So yeah, I just discuss first question.
Okay, ma'am.
So first question of week 2. So week 2, the due date for week 2 was 8th. So the date is already
Yes,
gone.
ma'am.
So I am discussing the same assignment which was supposed to be submitted by you. So due date is over,
Okay,
so I
ma'am.
can discuss that. So I'm discussing week
Okay,
2,
ma'am.
and I'll discuss half part of week 3, because I can cover only
Okay, ma'am.
that thing. So from the next time it will be balanced, hopefully. So I'll discuss week 3 half part and week 4 full. So that is the plan,
Okay,
so
ma'am.
that you can be
Okay.
benefited by this. But yeah, obviously that will be sample questions. Okay.
Yes, ma'am.
Okay, so this question I can just I can explain it again. So basically, in this first question, let P be a poset, and A B belongs to P such that A meet B exist. Then it has been asked, what can you say about this element A join A meet B? Okay. So I hope you are aware with these definitions. So is that question clear in general?
Yes, ma'am.
Okay. So yeah. So meet is basically A meet B is the greatest element. I'll change color. I guess that will be good. So A meet B is the greatest element of the set. Where T belongs to P and T is less than or equal to A and T is less than or equal to B. We can pick the greatest element, then it is done. So greatest element is that at most one element which can exist in the poset, in this subposet basically. And A join B will be the least element of the set. T belongs to P, where A is less than or equal to T and B is less than or equal to T. So the definition, I hope the definitions are clear.
Yes, ma'am.
Or you have any doubt, you can tell me on these definitions. Okay, so yeah. So then what has been asked, it has been given that A meet B exists. Now what can you say about A join A meet B? So let's see what is that element. So uh, A join A meet B is what? From the definition, what can you write? Least element of the set T belongs to P such that A is less than or equal to T, and A meet B is less than or equal to T from the definition itself. So I have used this definition, and from that I can just write least element of the set of all those T in P such that A is less than or equal to T, and A meet B is less than or equal to T. So this is meet and this is join. Now what can you say about this set basically? So least element of the set, all those T belongs to P such that, now just observe what is going on here. So here A is less than or equal to T and A join B less than or equal to T. Firstly, this makes sense only if this exists, because if there is no element of such kind, we are not saying anything. So this element exists, then only we are asking what is this set, right? So this element exists. Now you know that what is this A meet B is all those, let's say S belongs to P such that S is less than or equal to A and S is less than or equal to B. So what does this mean? If this element exists, greatest element of this, greatest element of, okay. So this, if this element exists, what does that mean? A meet B is less than or equal to A. Is this clear? So from,
No,
yeah, tell me.
no, ma'am.
No.
Once again,
Okay. So what I am saying, so what is this? A meet B is the greatest element of the set of all those elements of P. Let's say S belongs to P such that S is less than or equal to A and S is less than or equal to B. Okay, so join is
yes,
basically kind of intersection. Meet is basically intersection in the uh, what do we
set,
say? Yeah, set of inclusions. Like take the
set,
subsets. Yeah, subsets of let's
mm,
say square bracket n, and so basically take the power set
yes,
of n
mm,
and with inclusion. So in that case it's like intersection, and join is like union. And if you take divisibility one, so dn
yes,
comma
ma'am.
divisible one, what can you say about meet? So so meet will be kind of what? Meet will be kind of GCD, kind of GCD. I'm not saying that is exactly or something, but it is kind of GCD. And yeah, so if you take this set and join will be like LCM. So basically you are trying to, if you have two elements, you are trying to get the greatest element which is very near to those two elements, but is lesser than that. Okay, and meet is like you are taking the least element from upside, and least element, but it is bigger than A and B. Okay, bigger than like greater than or equal to A and B. So you are trying to get nearest elements from down and up. It's like that. So here,
Okay,
for example, A meet B is a set of greatest element in terms of those posets which we have read. So greatest element of the set of, if you want to say subposet, you can write of the subposet this S belongs to P such that S is less than or equal to A and S is less than or equal to B. So you are trying to get from the downside, you are going up and up, and you will stop at A and B. Okay, so it's like that.
Okay.
So that means the meat will always be less than or equal to A and B from the definition itself. Whatever S you will get, it is going to be less than or equal to A or less than or equal to B. It exists, so there is some element, that is for sure, because it has given that this element exists from the definition, from the question. So the conclusion is, so the conclusion is, I'm saying A me A meet B is always going to be less than or equal to A, even less than or equal to B.
Yes, ma'am.
Okay, great. So now use that thing. This I can keep. Now use this thing here. So you got so so for example I can write it again. So what did you get? Least element of this set T belongs to P. Now you know that this is going to hold always. Now you have two
Yes, ma'am.
conditions: A is less than or equal to B, and A A meet B is less than or equal to B. So if I just say this, uh, yeah. So if I just say A less than or equal to T, then this is enough, right? Because
Yes, ma'am.
yeah, so if this exists, then A meet B is less than or equal to T anyway, because this holds. A meet B is always less than or equal to A. So this set is basically with A. So now what does that mean? Least element of the set where T belongs to B and A is less than or equal to T. What can you say about this?
A is the least element.
Yeah, A is that least element. Very good. So you got that this is equal to A. Now what has been asked, that this element exists or not? You know that A is there, so this always exists. If A meet B exists, then this is going to exist always. So this statement is true. Okay.
Yes, ma'am.
Okay, great. Let's move to the next question. Let P be a poset. Okay, again we'll consider P to be a poset. So let's write, better to write with the symbol if you want. So this is a poset. Let A, B, C belongs to P such that, so it has been given that. So this is for some. So it's not like for every, for some. A, B, C belongs to P such that A join B, B join C, and A join B join C exists. Okay. Now, what can you say about this element? A join B join C. So, similar from the last part, can you say something on this?
We can write A
Yeah.
union A meet of B union C.
Okay. This is these are all joins. How will you write?
Joints means least element of
Sorry.
meet means least element means join means least element of the set.
Yeah. Join is like union and meet is like intersection. So join is
Intersection
always,
least
yeah. Yeah, least means least from the upside. So basically union is, so union is always what? Union is like, for example, if you take subsets, so h1 union h2 is the least set which contains h1 and h2, right? So in
Yes,
that
ma'am.
sense, so this is like least subset if you are in subset condition. I'm just trying to relate it with that because these notions we are familiar with, like we use it very frequently, and we know these symbols, these union and intersection. So I'm just trying to relate it. And so these
Okay.
union intersection is one kind of poset. So this is like inclusion, so it's like a powered set of x, if you want to write like that, or maybe even you can
Ma'am,
take.
I have one doubt.
Yeah.
Union means two sets we joined and intersects means we take only one element. And here we used join and meet. What is the difference between union and join and intersection and meet?
Okay, difference is, so basically what is that? Okay, so you have a poset.
Mm.
So you have a poset.
Mm.
Now, in this poset, so this is particular a definition for poset. In this poset, A join B. So for A B belongs to P, A join B is equal to the least element. I'll differentiate with what you have in your mind. So the least element of the subset, if you want, or you can write just the set T belongs to P, so it should belong to the poset such that A is less than or equal to, A is less than or equal to T, and B is less than or equal to T. So what has been asked? So you have this A element, you have this B element, you take something which is bigger than that, and
Okay.
which is the least in the sense that, for example, like you have the definition of cover, it's like that, the next element just next to it.
Mm.
So
Mm. Mm.
in that sense, it has been said, but I'll relate to what you have in your mind. But we are not saying this always exists. There could be a possibility that, for example, you have this set, you have the partitions, or maybe, yeah, for example, you have the partitions like this. You remember this?
Yes, ma'am.
Okay, great. So this is a partition. Now you have at this level 1 2 3. Now
One,
let's
two,
say,
three.
yeah, let's say you don't have anything above that. This is a subset of the all partitions, because what is not here, it is 1 2 3 is not here.
One, two, three is not here.
So let's say this is not there. So now you now if I ask this and this, what is the join of this? Let's say I am asking join of this element 1 2 1 2 3 and 1 2 3. Now what you will search? You will search for the bigger element from these two. I'll scroll vertical. Yeah. So uh, so you have this, for example. Now we are asking this 1 2, uh, what is the join of these two partitions? Now what will you search? You will search for the bigger element, because these two are different elements, so we have to search for the next one. So next one means some t such that A is less than or equal to T and B is less than or equal to T, right? So you are searching for some T which is above that, but there is no such element, and these are not
Yes, ma'am.
comparable. For example, if I ask 1 2 3, so there is no such element, so this does not exist. And you know that greatest element and least element need not exist in every poset.
Yes,
so
ma'am.
so
Yes, ma'am.
that is happening here. And
Mm.
let's take 1 2 3 join uh, 1 2 3. You take this element and this element. So can you tell me what will be the join?
One, two, three.
1 2,
Least element is one, two, three.
where is the bar, where is this vertical line?
One bar, two bar, three.
Okay, so firstly let's check is it or not. So you are asking,
Mm.
what is this set? You are searching for least element of the subset, or if you want to write set, T less than or equal to, T belongs to P such that, now what is your A? A is 1, 2, 3 less than or equal to T, and 1, 2, 3 less than or equal to T, right? Now is
Yes, ma'am.
now if you take, now you are searching for the least element, but it should satisfy this set property, right? It should be from the set. You are searching for a least element, but it should be in the set, right? So that means if you are saying this is your T, this is your least element, then this should hold, this should hold 1, 2, 3,
No, ma'am.
and but this is not true, right?
Yes, ma'am.
So this cannot be your that element. So what you are searching, as I said, you are searching for
Ma'am,
the,
in using as diagram, we are that lower element is least element and upper bottom of the numbers is a exist only unique element means
yeah,
that
yeah,
is greatest.
yeah, I got your point, but we are
Uh,
asking for the
uh,
least element of this set, not the full poset.
mm, okay, ma'am.
So we are saying, tell me
Mm,
the, so you have a class of, for example, 50 students, and we are checking the height of those 50 students. So we have some 7 foot
yes, ma'am.
people and some like 4 feet, 4 foot person. So but
Mm,
if we choose some 10 students from there, then it need not be true
mm,
that that 7 foot one will be there. That is not required, right? So we are
yes, ma'am.
asking from the
Mm,
subset, not from the biggest one. So that's why,
okay.
that is the difference. So we have been asked least element of this particular set. That's why I was writing subset, just to, uh, so in this subset means, so firstly what will you write? Least element of the set. Now let's write what is this set, so it will be clear. 1, 2, 3 less than or equal to T. 1, 2, 3 less than or equal. Let's see what is this set. I'm just writing, what are all the T's which are there, satisfying these two conditions. Okay, let's see. We have
Okay.
these four elements. So can you tell me what? Okay, first let's check. Can you put 1, 2, 3 here? This first element 1, 2, vertical line 3.
Mm,
Can you put here in this set? So I'm asking, will
yes, ma'am. Yes,
this?
ma'am.
Okay, great.
This set is
Yeah, we can have it because this is the same, so there is no issue, and this is the closed one. So one bar, 2 bar, 3 is definitely less than or equal to 1, 2 bar, 3, right?
yes,
So we
ma'am.
can have it. Can we have any other element? Let's say, can we have 1, 2, 3? So
And this element also less than or equal to 1, 2, 3 then.
yeah, it is true that this is less than 1 bar 2, sorry, so I can, this is true. One,
Mm,
2, 3 is, so the lower one should be the refinement. So 1, 2, 3 is less than
yes,
or
ma'am.
equal to 1 bar 2, 3. That's okay. But is
Mm,
it true
mm.
that this will happen? Is it true this part is true or not?
No, ma'am.
No.
It's no.
Yeah, there is no comparison because this
Mm,
1, 2, you cannot say this is the refinement or either combined. So basically there is no comparison between these two. That's why these comes in
yes, ma'am.
the same level with no comparison. So we
Yes,
cannot
ma'am.
say that. Similarly, we cannot say about this 1, 2, 1 bar 2, 3, and now 1, 2, 3 again we cannot have because 1, 2, 3 is comparable, so we can take T to be this, but not from here. So you cannot say this, right? This is other
Yes,
way
ma'am.
around. This is other way around, right? So
Yes, ma'am.
yeah, so we cannot have these things. So we have just one element in this set. So we have just one element in this set. That's why, so you have been asked least element of this set. You can have multiple things. If for example,
Yes, ma'am.
let's for example 1 2 3, and you have 1 2 3 and 1 2 3, and you have what has been left, this one. So for example you have this, and now let's say you have the full set 1 2 3 combined. So now if I consider this set, then I can put 1 2 3 also in this
Yes,
set,
ma'am.
because that is bigger than
Yes, ma'am.
these two elements.
Thanks to.
Now
Mm.
now search for the least element of this set.
Yes,
Then
ma'am.
what?
One, two,
1 2
three.
bar 3, right?
Less than
So
or equal to 1, 2, 3.
yeah, uh, yeah, so you in this set you know that this is the least element, because 1 2 the combined 1 2 3 is bigger than 1 2 bar 3. So
1, 2 bar 3.
yeah, so that is the thing which has been asked. So you will search for the bigger one, but the lowest bigger. That is the thing. So you have, for example, two elements. You will search for the bigger one, which is just up from those two.
Okay.
That this is least element. That's why we are saying of this set, not the full poset. That is one which we have discussed in general. Okay. Similarly, if
Okay.
we say greatest element, now greatest element from the down part, like you are coming to A and B from the down, from like you are going increasingly. So it's like greatest element of the set T belongs to P. Now if I ask 1 2 3, now you are asking for meet is like intersection. 1 2 3, this one. So that will be the greatest element of the set T belongs to P, such that 1 2 3. Now you are taking the least elements. T is less than or equal to 1 2 3, and T is less than or equal to 1 bar 2 bar 3. So that is the set. Now you are coming from the down part. So you are saying you take the greatest element which is very near to these two elements, and there is nothing in between. That is like there is nothing in between this T, this greatest element, and the A and B. Like there could be one between A and that element, but from the B it should be uh, it should be least. It should be the greatest basically. So yeah, from the what I yeah. So can you tell me what will be this set? So can you tell me T's which will come in this set? For if you have the full partition set. So you have this full partition set. So all those T which are less than or equal to 1 2 3, and which are less than or equal to 1 2 and 3, like 1 partition 2 partition 3, or maybe 1 bar 2 bar 3. What will be the element? So you are searching for all those T which satisfy these two conditions. Now let's see what are all the elements which are less than or equal to 1 2 3. Now 1 2 3 is here. There is nothing below that, right? So there is no T which is below that, but that element itself can come. So for this T less than or equal to 1 bar yeah, 1 bar 2 bar 3, this is satisfied by this element only, so you can take T to be this. And now let's check if the other condition is satisfied. t is less than or equal to 1 2 3. This is true if you take t to be this 1 2 3 less than or equal to 1 2 3. Okay, so you can only take one element, and now greatest element of that set means greatest element of this. So you will get greatest element of this set is just 1 2 3. Is that clear a bit, Mahalakshmi? Okay, you can tell me if you have any doubt, but okay, let's continue. So which the thing you asked about.
Yes, ma'am. Yes, ma'am.
Okay,
My mic is off.
okay. So yeah, great. So this is the thing. Now intersection, which you asked, intersection and union thing. So so now consider the subsets thing. So subsets of, for example, let's take this subsets of this. Now you take one, you take two. For example, if I ask, now this is a poset, right? Subsets of n, so power set of n with the inclusion. So less than or equal to is like is your inclusion thing, right? So for example, if I ask this 1 comma 2, or maybe let's take this, if I ask tell me the meat of this. So meat of this is what you will search. You will search for the greatest element from the definition. So basically, if you want to form the diagram, this is 5, here you have 1 2, you have 1 3, you have 2 3, you have 1 2 3, and 1 2. So it will go here, sorry, will go here, here 2, here 2 3 3. So this is the so if you take n to be 3, then you have this as the Hesse diagram, right? Now uh, uh, now can you tell me what will be the meat of 1 and 2? So greatest element of the set of the poset, basically t belongs to p such that t is less than or equal to 1. So basically less than is like t is contained in the set 1 and t is contained in the set 2. Okay, is that clear? So you are searching for the greatest element of this set. So what you are asking, you have these two elements. Now tell me the greatest element from this set. This set means you consider all the elements which are lower than these 1 and 2. Okay, so what are all those elements? This is just 5, right? So you have this set is equal to 5, set of the set with the empty set in it. So greatest element will be what? Will be just 5, because there is just one element, so you have nothing to compare. Is that okay?
Yes, ma'am. Yes, ma'am.
Now, so this is basically what? This is basically your intersection.
Intersection.
Yeah, this is your intersection. So if you take this particular subset, this particular
Okay.
poset, then in this poset, you're less than, sorry, in this poset, your meet is actually intersection and join is actually union in this poset.
Okay,
So
ma'am.
so
Ma'am. Okay,
intersection,
ma'am. 1
yeah,
1 comma 2, 2 comma 3. The greatest meet of 1 comma 2.
and 1 comma 3, right?
This 2 is
Hmm.
1. Correct, ma'am?
Yeah,
Least
exactly.
greatest element of.
Yeah. So yeah, let's see if this is, so this is from the again intersection. You can check with this definition. This is greatest element. So what you are saying, greatest element of the set T belongs to P such that T is less than or equal to 1 2 and T is less than or equal to 1 3.
1, 2,
Okay.
1, 3.
Now
One
you,
more example, ma'am.
yeah.
1, 2, 3. The
Hmm.
bottom one. 1, 2, 3.
Yeah.
Meet of.
Hmm.
Not this one. First, last one.
Okay.
1, comma
This
2,
one.
comma 3.
Yeah. Hmm.
Uh,
Yeah,
and
this one. Hmm.
3. Meet of 3.
Yeah. What will it be?
What? The greatest element of the set.
Yeah.
5
So greatest element. No, no. Now you are
is
searching.
5.
Wi-Fi.
Uh,
So let's see. So
no,
you
no,
are.
I'm asking.
Oh, you are asking. So will it be 5?
Uh, mm,
So check whether this is true or not. So you are saying this is greatest
mm,
element of the set T belongs to P such that T is less than or equal to 1 2 3 and T is less than or equal to 3. So you are basically saying you consider all the elements which are less than or equal to this and which are less than or equal
mm,
to 3. Now you can take
mm,
5 firstly, ST, right, in this set.
mm,
You can take
mm.
greatest element of the set 5. Firstly you can have 5. What else can you have in this set?
3.
3, exactly. You have equality. So 3 is contained in 1 to 3. 3 is contained in this set. So you can take
Yes, ma'am.
T to be 3. So
Mm.
T means the set,
Thing
subset T.
belongs to the poset.
Yeah. So
Mm.
greatest element of this set. Now you know that of this set
Eh,
greatest element will be just 3, right?
3.
Because
Mm.
there is a comparison. For example, if you just have 2 3, then there will be a problem. 2 and 3, you cannot have greatest element of those two elements because they are incomparable, right?
Okay,
So
ma'am.
there will be some examples
Mm.
in other questions. You will get more knowledge of this. But yeah, that is the
Okay,
thing.
ma'am.
So with this poset, your intersection and so intersection will be same as meet and union will be same as join. That is the thing.
Join.
Yeah. From the Hesse diagram,
Okay.
you have these two elements. Consider all the less than elements. For example, as you taken this, so you can take 5 and you can come to 5 anyway, in any case. So for
Okay,
this
ma'am.
also 5 is
Okay.
there and 3 is there. So there is a connection
Okay.
between these. So it's like that. Just try to rigorously do that. So it will be like you will get more knowledge on this.
Okay, ma'am.
Okay, great. So, in the question, what has been asked? So that was the question. Uh, yeah. So you have this. So what is A join B join C? If I try to tell you with the, just erase this part. So actually we can do it directly, but let's do it rigorously a bit so that. So so this is like so there is a join thing. So I'm opening this join. This says least element of the set A, all those T belongs to P such that uh, A join B is less than or equal to T and C is less than or equal to T. From this set, from if I open this join, so it's like this element and this two elements are there.
Mm.
You have this element and this element. So is that okay? Now least element.
In
Now what
in
can,
join.
yeah, A join B and here you have C join. C is now now let's see. If I say A is less than A join B is less than or equal to T. Now you can open it,
So,
right? You can open that
yes, ma'am.
and you are already asking about the least element, right? So
Mm.
outside also you are asking for the least element, so and this element exists, so it's not like there is no element of such kind. This element exists, that's why this definition makes sense. So you can actually
Okay.
write this is less than or equal to t, b is less than or equal to t, and this comes here because a join b means what, all those elements. So
Not
least,
exist.
yeah, if this exists, so this exists, so that's okay. So s belongs to p such that a is less than or equal to s and b is less than or equal to yeah, s. So you can expand this part by this because you are in general also asking for the least element, so that this makes sense. Now you take, now what can you do, again you are asking for the least element, you can combine these two things, right?
Yes,
Least
ma'am.
element of the set, combining means you can write it like a less than or equal to t and b join c, sorry, yeah, it's join not meet, b join c less than or equal to t. You can combine those, and in general you are asking for the least element, so you are in a good state. You cannot do for like for meat, because for meat you need to have greatest element, so the set will
Mm.
not be okay with that. So now you have least element of t belongs to p such that, and this makes sense because this element exists from the question.
Yes, ma'am.
Question says this is there, this is there, and there is this third thing you can use here. So least element of this set, what can you write it like? You can actually write it a join b join c. So you have these two
Fancy.
elements and that exists. So you are done. So this element exists, so this element has to exist. So this statement is true. Okay?
Yes, ma'am.
And in general, if you see the notes, so this is basically the proof of that part. So it says you, this is in general true. If you have like this is equal to this b join c, and a, for this also, for meats also you can write it like this. So these are always true. So yeah, done. You can directly use these results.
Yes, ma'am.
Yeah, is that okay?
Yes, ma'am.
Okay, let's move to the next question. Recovering the partial order from lattice operations. So basically, what is a lattice? Do you remember the definition? Okay. So lattice says this is a poset with, for all, with the extra condition, the condition, the following condition: for all x y belongs to lambda, x join y and x meet y exists. God bless you. So for all x y belongs to this lattice, x join y and x meet y exists. So this extra condition which we are posing on this, on a poset. Then we say that this is a lattice. Okay. So this is the
Okay.
definite. It should exist basically. So for example, when we have taken 1, 2, 3, 1, 2, 3, and 1, 2, 3, and you have 1, 2, 3 here, here. If you just have this, then this is not a poset, not a lattice, because you cannot have 1, 2, 3, and if you want to join that, so if you want to join these two elements, there is no any element above that.
Not.
So this does not exist. Does not exist. Okay. So there is no
Yes,
such
ma'am.
element here, so you are done. So this is not a lattice. So there are posets which are not lattice. Okay, so so what do we have? If lambda is a lattice, then and xy belongs to lambda, which of the following equivalent to x is less than or equal to y? So you have given you have this condition, y sits above x. So what can you say about what can you conclude? So basically, what is this? X meet y. So what will be x meet y?
Least element of.
Yeah. So from the definition, what is this? This is this is greatest, right? This is the greatest.
Sorry.
Yeah,
Ah,
greatest
ah,
from
ah.
down. So greatest element of
Of the
x
set.
and yeah, sorry, of the set t belongs to p
It
such that
belongs to P.
yeah, and
X less than or equal to T.
yeah, exactly, and y is less than or equal to t. Now you have given that y sits above x, so these are comparable, and x is less than or equal to y. So from
Mm.
these two conditions, if y is less than or equal to t, then x is definitely going to be less than or equal to t, because you have this condition.
X is one.
So
X is less than or equal to T.
if this happens, this implies x is going to be
Implies
less.
X is. Mm.
So so you can basically you can
X is
basically
the greatest.
yeah, x is the greatest, so you can just uh, yeah, greatest element of what I was saying, yeah, if y is less than or equal to t, right, yeah. Sorry, what I just said, I said if x is less than or equal to t.
If Y is less than or equal to T, implies X is less than or equal to T.
Yeah, so I can actually remove this part, right? So this is greatest element mm, what am I missing? So basically, what can I write? Which condition I can remove here, basically? Ah, right. That is the mistake. I was saying what exactly I am doing wrong. So greatest element of
T
yeah,
is
t
less
is
than or
less than
equal
or
to
equal to
X.
x. Yeah, exactly. So
T is less than or equal to X.
so now it makes sense. So if you have, because that was so yeah, if t is less than or equal to x, then this implies, now you know that x is less than or equal to y, so you can this
Yes, ma'am.
implies t is less than or equal to y. So this, that means greatest element. So basically, if you write this, then the other condition anyway holds. Okay,
Yes, ma'am.
so greatest element
Mm.
of this set just is just x, because all those t which are less than or equal to x, so you can and you are taking the greatest element, so just pick x, then you are done, right?
Yes, ma'am.
So whatever you have, x is there and you are done, right? So
Yes.
so in your question, so x join y, x meet y is equal to x. So basically, just think of the least part. Okay. Now,
Yes,
for
ma'am.
this x join y, what it will be? Can you tell me directly, or maybe if you want to try least element?
Y.
Y. Exactly. So this will be y, because least element of the set t belongs to p such that x is less than or equal to t.
Not equal to T, Y is less than or equal to T.
Yeah, so this implies this, so you can just remove that, and you will just get this condition and you are searching for least element, you can just pick y. Okay, very good. So you have this and this. Okay, let's move to the next question then. True or false? What is a distributive lattice? Distributive lattice. So you know what is a lattice. Now let's move to what is a distributive lattice. So distributive lattice, from the definition, so distributivity is like, can you expand? Now you have just two operations, you have two operations, meet and join. So
Yes, ma'am.
can you expand meet over join or not? That is the question. That is the definition basically. So if that happens, then you have distributive lattice, otherwise not. And you have, for all a b c belongs to p, or maybe lambda if you want to write. So the distributive lattice lambda, and a join b meet a join c. So these are two conditions. So the distributive lattices, it has been asked like that. So if these two conditions are there, then for every ABC in the lattice, if these two conditions hold, then this will set to be a distributive lattice. So let's see with pi 3 what is happening. So what is pi 3? Pi 3 is partitions of 1 2 3 set. So we are partitioning this. So partitions, you know that 1 2 3, just
Yes,
consider
ma'am.
that we have taken this as a used to example now. 1 3 and 2. So you have this, here this, and here you have 1 2 3. Sorry, not this, combined. So you have this. Now what is a distributive lattice? That is the point. Sorry, will these two conditions hold here or not? That we need to check. So let's see
Okay,
what
ma'am.
can we take. Okay, so so a join b join meet c. So these two conditions, so we have to actually check for every element. So you know that if you take so just to, now you will get used to with this meet and join, I hope. So for example,
Yes,
tell
ma'am.
me, if you take these two elements, what will be the join of these two elements?
One bar two three.
Yeah, exactly, very good. Similarly, if you take join, you will get this element here. With this element, you will always get this above one. And if you take meet of this and this element,
One one two three. One bar two bar three.
very good, yeah. So this will be your meet. So now you know the operations. Now if you have this element and this element, so you have 1 2 3 and 1 2 3. Now what will be the meet join of this?
Does not exist.
uh, Check it if you can see. So you are asking for the greatest element which exists above that, sorry, least element which is above these two elements. So from the definition, what is, sorry, least element of the set, all those t belongs to p such that t is less than, so not less than, it is above that join here. So you have 1 bar 2 3 less than,
1 2 3 less than or equal to t. 1 2 bar three less than or equal to
yeah,
t.
exactly. So in this set, what do we have in this set? Which element can you put? So a t, like a element of poset which is bigger than these two elements.
1 2 3.
Yeah, so 1 2 3 you can definitely put. Now least element of this set, this is just 1 2 3. So you have the element, because
Mm.
if some number exists if there is a variety,
Yes, ma'am.
like there will be an example in these questions, there you will see there are many elements, so you cannot compare, and that's why it will not exist. So that possibility will come. But for example, in this situation there is just one element. So if there is one element, then it is going to be least. If there is a variety which is not comparable, then there will be a problem. So here
Okay.
in this situation 1 2 3 will work. So that will be the thing. And what about this meat? If you want to see meat, so an element which is
One,
lower.
two.
Yeah, which one?
One bar, two bar, one bar, two bar, three.
Exactly. So it's like that. So very good. So this is the situation. Now can you search which is a which could create a problem? So let's see. Okay, so you have you need to calculate this side, and you need to calculate this side. So I'm just considering first one. So actually I know the answer, so I'll use that. So basically you need to check all of it. Now always
Yes,
problem will
ma'am.
come where there is a incomparability. So basically that can create a problem. So if you are searching for that, just try with where there is a problem kind of stuff. Okay, let's see. So I don't know if I remember it correctly. I'm trying, but let's see. So you have 1 2 3. Let's take that. And here you take the second part, or so let's take this, and b join c. Okay. So okay, I think the second one I remember, so I'll use that. So you have this. You are searching for this. So which ABC you will need to pick, that is the question. So basically you should try all. That's why that is the only way where you can say that this is a distributive lattice or not. Because if that is a distributive lattice, then you have to calculate for everything, you have to check for everything, and if it is not, then there should be a counter example. So I'm saying this is not a distributive lattice. Which example I'm giving? So for example, in this situation, so if you take A to be 1 2 3 and B to be 1 2 3, and other side you take 1 2 3 and you take 1 3 2. So you are taking this to be A, this to be B, this to be C. So you will get here, now you are taking you are trying to get the join, sorry, meet of this. Firstly, what will be the value for this join of these two elements?
One, two, three.
Yeah, and join, and with these two again you will get 1 2 3. So
One, two, three.
meet will be just 1 2 3. Now let's check the other side. Other side says, other side is this. So A is your 1 2 3, and join you have B. uh oh wait, yeah, B meet B meet C. B meet C means 1 2 3 and meet 1 3 2. So 1 2 3, you have this, and with this what will you get? The lower part. So you will get
One
1.
bar, two
Yeah,
bar.
exactly. So with
One bar,
these
two
two,
bar, three.
yeah, exactly. And the join will be, so join of this element and, yeah, this element. Join of this. So join of these two elements. So the,
One bar, two bar, three.
oh, join. So you have this 2 3 and
One bar.
1 bar 2 3.
One bar, one, two, three.
Yeah, so because this stays above that, so anyway if you take any element
Yes,
and you
ma'am.
are asking for the join,
Mm.
so that is the problem. This is not equal to this which was
Yes, ma'am.
required. So the counter example usually exists where there's a incomparability thing. So I search for that and you can actually try. So yeah. Anyway, if that is true, you have to check all the possibilities and you have to come up like these are always equal. So there you will get if there is a like there is a problem. So here, as in this example, so this is false. This is not a distributive lattice.
Distributed.
Exactly. Okay, let's move to this question. X is equal to 1, 7, 2, 4, 3, 5, 6. So this is, we are in the partition of set 7, like this. 7 square bracket 7, partitions of this set, partitions of this. Okay, so x is this and y is equal to 1, 3, 4, 6, 7, 2 and 5. This is, these are these two things. Can you tell me what will be the meat? So now let's try what is the meat. Meat is basically greatest element of the set, all the t's belongs to, or maybe I'll write pi 7, such that uh, t is less than or equal to x and t is less than or equal to y. Okay, so these two things,
Yes,
greatest
ma'am.
element of this set. What can you say about that? So so x is so let's write what is this set basically. So let's forget about greatest first. What is this set? All those t belongs to pi 7, which for which t is a refinement of 1, 7, 2, 4, 3, 5, 6, and t is a refinement of 1, 3, 4, 6, 7, 2, 5. Okay, all those t you need to consider. So firstly let's see what are all these t. So for this what should happen, you can split which are already splitted, right? So you have 1, 7,
Yes,
2,
ma'am.
4, 3, 5.
3, 5, 6.
Yeah, so what can you take as your t? So you can, what can you
And
do, you can separate this. Okay, and you can keep all the other stuff as it is. You can you can keep separate. So there are many possibilities. I can write one or two. Okay, so 3, 5, I have separated this now. Okay, now with one separated 7, again you can do with two separated 2 and 4 are splitted already. So you have too many possibilities, just the refinements you can have, right? These could be the
yes, ma'am.
possibilities for t. Now for this set, so you have to have t which satisfy both of these conditions. So you have 1, 3, 4, 6, 7, this. Okay, now you're searching for all those elements which are, so you can refine basically this set. So 2 and 5 are already in the singletons, as singletons. So you have to refine 1, 3, 4, 6, 7 basically. So we have to check which are the refinements for both the elements. Okay, here it says 6 is already separated. Here it says 2 is already
Yes, ma'am.
separated already, 5 is already at singleton position. So 2, 5,
Yes,
6
ma'am.
will come already in the separated line. Okay, because
Yes,
if you
ma'am.
take the
Mm.
refinement, 2 and 5 singletons will always be at that position itself. So these three will already be like that. Now what are all the possibilities for 1, 1, 3, 4, 7 basically?
And three,
Okay,
four, seven.
yeah.
Mm.
So 1, 3, 4, 7. Now you see there is two separated already. So you are saying, you whatever t you are considering for this set, whatever t you are considering for this set, 2 has to be in as a singleton. So 2 is separated already, 6 was already like this. Now in the refinement you
Five.
can, for 2, 4 you can only separate 2, 4. That is the only possibility, right? Either it will be in the combined position or it will be in the single as singletons, right? These are two possibilities for
Yes,
2,
ma'am.
4. But 2 is already as a singleton because it is coming from the other one, right? So 4 is
Yes, ma'am.
4 has to be separated. There is no possibility for 4 to go anywhere, right?
Yes, ma'am.
So 2 and 4 is separated already again. So these four are settled.
Same
Now
3. Yes, ma'am. 3 also.
3 also, exactly. So 3 also it will happen. So you have 2 and 3. Okay, now what is left? 3 is gone, 4 is gone. Now 1 and 7, 1 and 7 are there. So 1 7 is here and 1 7 is in the same
Same.
block basically. So you can have possibility for 1 7 combined. You can have
Yes,
the
ma'am.
separation. So these two things only you can have, right? So
Yes, ma'am.
7 separation means basically it should come behind. Yeah. So the in the set, as in the set you just have these two elements. Now you need to
Yes, ma'am.
search for greatest element of this set.
Greatest element of the set.
So what will it be? So in between these two, which one is greatest?
In this set, 1 7 bar, 2 bar, 3
Yeah.
bar, 4 bar, 5, 6.
Yeah, this is your greatest one, right?
Greatest element.
Yeah. So that will be your answer. So this will be 1 7 1 7 and everything separated 4 5 6. So as a technique, if you want to see what is the technique, so exactly what we are doing, if the things are in different blocks, so it has to be in different blocks in the join. So in the meet, it should be in the separate blocks. So just take all the separations you have. So 2 5 is separated, 6 is separated, so that singletons are there. Now when 5 is there, then 3 5 has to be in separate, like in as singletons in different blocks basically. So if you have the same
Yes,
block, if the two elements are in the same block for x and y, then only you have the possibilities. Otherwise you will have the
yes,
singletons basically. If these are in different blocks, and in one it is in same block, and in the other one it is these are in different blocks, then that will come as separation. So different blocks, so
ma'am.
one with different blocks, two elements basically. And in one and second one, these are in same blocks, then it has to come as singleton basically. That is the rule. Okay. So this is the property for meat. So we have
Yes, ma'am.
gone through the process. So from process itself you can observe the pattern what is happening, and you can come up with a, like, short not shortcut basically. What exactly we are doing, we can just, if we remember, if we understand, then we can directly do that. So that is the rule. Now what will be the join? That is the question. Now next question is with the same thing actually. So you have x to be 1 7 2 4 3 5 6, and the other one is 1 3 4 6 7 2 5. Okay. Now you are it has been asked what will be the join.
Least element of
Yeah,
the
least
set.
element. Now you have to combine things because you are asking for the
Combine
bigger
things. Yes,
things.
ma'am.
So this is pi 7, and you have t is less than or equal to, sorry, and other way around.
1 7 less than
Yeah,
or
exactly. 1 7 2 4 3 5 6 is less than or equal to t, and 1 3 4 6 7 2 5 is less than or equal. Yeah, right. So this is the thing. Now you are asking for the combinations. So you are searching for the
mm.
elements which you can combine. So now
Mm.
combinations, and 1 3 4 6 7. So the other one is looks okay because it is already in the combined position. Just two elements are as singletons. So you can try with this.
Yes,
You
ma'am.
can combine. You can have the same element first. Second thing, now you see, if something is already in the same block, then it has to be in the same block, right? So
Yes, ma'am.
so 1 3 4 6 7 will be there. Now you can have, so first possibility is 2 5. Second possibility is you combine with 2 and keep 5 as separated, like 5 as singleton. You do with 5 this, and the other is like you just combine everything. So these four possibilities are there, right? Now
Yes, ma'am.
for this, so I'm searching for the possibilities which are like less than or equal to t. So t could be, now you are combining these. Okay, so for combination, what everything you can have. So firstly, it says if you combine two, if you combine 1 7 or anyone with 2, then 4 will come anyway. So
Yes, ma'am.
what it is saying, it is saying if you combine 2 with any of the block, this block, if you combine the second block with any of the block, 4 will anyway come, right? So if you have any block, let's say you are combining 2 4, then 4 will come anyway. So in this situation, in the second one, 4 is already in one block, so 2 will have to be in the same block. So if two
Yes, ma'am.
elements are in the same block, that will have to be in the same block for the bigger thing. So it says you cannot have this option because 4 is there, 4 and 2 are in different blocks. That cannot be a possibility. So that cannot happen. And similarly, this cannot happen, right? There are two possibilities left now. Okay.
Yes, ma'am.
Now again, you see this 3 5 thing. These are in same block. Then the bigger one will be, then the for the bigger one, 3 5 will have to be in the same block, right? So for this
Yes, ma'am.
also, so you have to pick all those options which for which 3 and 5 are in the same block. So in this scenario, this cannot come, the second one, 1 3 4 6 7 2 bar 5, you cannot have that, right? Because 3 and 5 has to be in the
Yes,
same
ma'am.
block. So the only option left is
Same luck.
this. Yeah, the all
One,
in the
two,
same
three, four.
block. So you have 1 2 3 4 5 6 7. So the answer, so there is just one element, so least will be this element only. Okay, so this is your join. So basically for join, you search for if something is in the same block, that will stay in the same block for both of the elements. So you just search for all those elements for which you have the same block thing. Okay, great.
Okay, ma'am.
So that is your answer. Okay, let's move to the next question. You have x 1 2 5 6 3 4 7 8. So this is so you are in pi 8. Now if you check the notes, so this is Krevrer's order reversing pattern. So basically order reversing bijection. So basically this is a bijection which reverses the order. So you have some, for example, pi 8, you are mapping it to pi 8 opposite. So opposite is what is this posset? This posset says,
Inverse.
yeah, not inverse means, yeah. So if you have two elements with this relation, then in opposite it will be
Then
this.
y,
Yeah, exactly, the reverse.
x is greater than.
Exactly. So the order will get reversed. So that is this opposite. So which element should map to this element? That is the question. So phi of x will be what? So there is a rule to do that. So that will come with this non-crossing thing, that actually helps in defining a bijection from this element to this element, because we are saying bijection, like, okay, so from that bijection, what will happen, that is the question. So that bijection, if you see the notes, I'll because that is something precise. Yeah, 7 8. So and you change, you write 1 2 3 4 5 6 7 8, you write with different color. Now from pi, so for pi 8, so for example this element x, where x will go, so that is the question. So you join the elements if there is a relation. So basically you are not a graph, but you're just trying to have it in the cycle thing. So 2 5 6 in the same block, so 2 5 and 6 will be connected, one is separated, 3 and 4 are in the same thing. So I'll write, okay, this 4, okay, right. 3 and 4 are connected. Now 7 and 8 are connected. So 7 and 8 are connected. So this is like that. So this is the blue thing is showing what is your x. So from this Crever's order reversing bijection, it maps it to, you map the red ones, so the other map basically in this opposite thing. So you have the element to be, uh, you join the like connections, you draw the connections only if there is, if it is not crossing the blue lines. So what you can have this, right? The biggest 7 cannot go anywhere because you cannot cross it. Similarly 2 4 you can have, but 3 and 5 will not go anywhere because it has to cross 5 6 line, it has to, 7 has to cross 7 8 line. It's like that. So this pi x should map to according to this. So 1 is coming separately, so you write 1 as like this. Oh sorry, not 1. Where is it?
168.
Yeah, 168 will come in the same part. Then 2 4
2, 4,
3.
3 bar, 5
Yeah,
bar, 7.
yeah, exactly. So this will be your element. So this is from this particular order reversing bijection. So this is the way to do that. So that will be your answer. Yeah. Okay, great. Okay, let's move to the next. Yeah, this was the question regarding distributive lattice. So you have this lattice distributive. Okay, it has been asked whether this is a distributive lattice or not. So again, try to have like something which are in incomparable situation. Again, you need to check whether this is true or not. Oh, I should not use ABC. Because so let's say y is there. X meet y, join X meet Z. So this is your question. So yeah, the poset in this figure, whether this is a distributive lattice or not, and the other property again is this. Yeah. So here, okay, I am again giving you the answer. So it's like, again, as I said, try to have like incomparable things. So C is not comparable. There are two streams you have. Okay, streams as in like chains you have. There are two chains you have. Try to have the different thing and try if you can. So if something is in the same chain, it will follow. Distributive property will follow because if you take two elements, then the join will be the bigger one, and if you take the meet, then the lower one will be the join. So if there is a connection, direct connection, then there is no issue. So in chain things are pretty good. But if you take like this, so for example, yeah, so for example, in this situation, if you take A, B and C, then if just check what will you get. So you will get a. Now what is B join C? B is here, C is here. So you are trying to have the least element from the set, which are all the elements of poset which are above B and C. So A cannot come. So above there are two elements, A and I. Okay. So A cannot come and B and C cannot come because these are incomparable. So A cannot come because C and A has no relation. Those are incomparable. So you need to have all those T such that so such that this property holds and this property holds. So so T you can only have this element I. So you have I, you take this I. Okay, so that if there is just one element, then it has to be least or greatest, whichever thing you need. So A join, sorry, A meet I will be, so you have A and you have I. Now there is just this direct connection. What will be the join?
Oh.
Sorry, meet. What will be the meet?
A.
A, exactly. Very good. So now you check the other part. I hope this should be the this should be your one of the answer. So you have A join. So you have A meet B. So A meet B will be what? So you have A meet
B.
B, exactly, and other side.
A meet C.
Hmm.
0.
Yeah, A meet C is just
O.
O. Oh, yeah, exactly. And B join O will be
B.
B. So these are not same.
Mm.
Not same. So there is an issue. So just try whenever you are trying to check it, just try if you can have the things within comparability, then well and good. Otherwise, you should get the counter example. Yeah. Okay. So okay, let's move to the next question. Every chain is a lattice. Yeah. So every
Mm.
chain. So what do you think?
Yes, ma'am.
Yeah, actually.
X.
Hmm. Yeah. So X. So basically, if you have two elements,
X, Y.
yeah,
Mm.
exactly. If you take two
Just
elements,
element X, Y.
hmm.
So least element is Y and greatest element is X, both and exist.
Yeah. So if X is less than or equal to Y, then the meat will be just the least element, the lower one,
X,
and join will be the bigger one.
X, Y, Y.
Yeah, exactly. So, because you know that in every chain there is a comparison. So, if you take any two elements of the chain, then there should be one of the conditions. So, whether x or less than or equal to y, or y is less than or equal to x. And in both the cases, you can get easily what is your values. So, x and y exist, so their meet and join will exist. Okay?
Yes, ma'am.
Yeah.
Mm.
So this is okay. Okay. Yeah, let's come to this question. Okay, let v be a vector space over a field K, okay, containing linearly independent vectors E and F. So you have two vectors E and F. This belongs to your V, which are linearly independent. So there is no relation between them. Vectors. And G is your E plus F. Now consider the one-dimensional subspaces KE, KF and KG. Okay. And consider the lattice of subspaces of V. Okay. Lattice of subspaces of V. Yeah. Lattice of subspaces of V is just you have something like you have subspaces of V with inclusion. So one is contained in another if that part is there. Okay, if that vector space is contained in the other one. Okay, so this is the poset. Now whether this is a distributive lattice or not. So lattice, so let's check if that is a distributive lattice. You can check, so it has been given that this is a lattice, so you can assume that, and you can check also this forms a lattice. Now for distributivity, again you need to check such kind of things. So whether this is a distributive lattice or not, that is the question. Let's check the second part, because they have particularly given something. Okay, so let's check if this thing is true. So uh, kg this meet ke join kf, what it will be? So kg you have. Now what will be ke join f kf? So this is one dimensional vector spaces. So join will be just like the bigger one. So basically this will be what? which the subspace which contains
K.
element E and F. What it will be?
Yep.
So it's like a union kind of thing
This
means.
E. Both K.
Yeah, so span of E and F. So there should be a vector space. Vector space
Mm.
which contains this. So you know that if there are two elements, then the full vector space thing will be there, right? So span of this, span of E and F. Okay,
Mm.
span of this set. Now kg intersection span of E and F, what it will be. So firstly let's check what is span of E and F. So E and F elements gives G. Okay, so G is there, so G
Mm.
belongs to a span of E and F. Okay, E and F are linearly independent vectors, so span so this has to be two dimensional. Basically span of E and F will have to be two dimensional, because E is not in the form of kf, or F is not in the form of ke for some k, like small k. So the span kg intersection is like meet span of EF will be what? G is there. So kg is going to be there. So basically G is there. This implies kg is a subset of span of E and F. And this itself is a vector space. So you are taking kind of intersection. So you will get just kg. So this part is true. This smaller one. Okay. What about the other part? Just a second. What about the other part, right?
KG meet A.
Yeah, kg meet A. Yeah, so they're asking,
Join.
yeah, kg meet ke. Yeah, join ke, kg and kf. So you have kg and kf. Okay, so
Mm.
what about this? So kg join ke what will be what? So you are saying join. So again, if you see, g is equal to e plus f. So since E and F are independent, so G and E has to be independent, because otherwise if E not contains, if KE is contained in KG, or maybe KG is contained in KE, then the bigger one has to have F element, which will be a contradiction, because E and F are independent elements. So in both the cases, so basically if E and F are independent, are linearly independent, then E and G has to be linearly independent, or F and G has to be linearly independent. So any two, if you pick, those going to be linearly independent, because otherwise if E and G are dependent, for example E is bigger than G, like Ke is bigger than Kg, then F has to be there, because E and G are in the same set, same vector space, same one dimensional vector space, then F has to be there. But it will contradict the property that these are linearly independent, E and F are linearly independent. So this will be span of kg, uh, span of, sorry, not kg, span of G and E.
G.
Yeah, and similarly this will be span of G and F.
G. Okay.
And in the intersection, what will you get? Span of just G, because
One of G.
yeah, if you take the intersection, E and F are independent, so this has to be true. So this will be just kg. So
One
these
of
are
this
same.
KG.
Yeah, but I think there is an issue in this question. So the issue is kg, this ke, this kf. If you are checking this, you should check it with this. Okay, so if you have kg meet ke wedge, join kf, then you are checking whether this is equal or not with kg meet ke, kg meet kf, right? You should check it with this.
Mm.
But these are reversed actually. So these are equal, but that is not something which was asked, which was required, right? Because if we want to check distributivity, then we have to check whether this statement and statement are equal or not. Okay. And
Okay.
are you getting my point? Because if you see this,
Yes, ma'am.
this should be checked with kg wedge, sorry, kg join, ke meet kf. But that is not something which we did. So this should be asked, and for this should be asked. Okay, anyway, let us do that. So we should actually calculate this value I'm saying. Okay, let's check what is this value. If the this is equal to kg, then this is okay, but we have to check all the possibilities again. So kg meet ke, what it will be? Because g and e are independent, so that should be just phi. That's not phi, that should be just zero element, the zero vector space. And this will be kg and kf are linear, g and f are linearly independent, so this should be 0. so the
Zero.
so the join will be 0, right? So these are actually
Yes,
not
ma'am.
equal. This is not equal to kg, so this is not distributive, not a distributive lattice. And the other statement, this part is true. Oh wait, span of e and f. Oh, right. No, wait, 1 second. So, okay, okay, whatever it is, let's check what is this value. That is another thing. So, this should be span of E and F or not? That is the question. So, this should be span of G and E. This should be span of G and F. So, in the intersection, oh yeah, intersection should be not this. Uh, Intersection should be span of G and E and span of G and F. Since you know that G is equal to E plus F, so you are just saying E and F, what is the intersection of those? So you are saying span of E and F basically.
Okay.
So that is something you are doing. Okay. Anyway, so that is something which is again not equal. So not equal or not, but the point is this should be checked. Okay, this should be checked. So what should I say? Like both of these statements are not actually right. So this is just not a distributive lattice. Or you just stay. Sorry, actually you can take this option, and that's okay, because it says this and this is true. So uh, this is not equal to this, that is a different thing, but these statements are itself true, so you can say that this is not a distributive lattice, because this is equal to kg and this is equal to span of ef, and there are other two statements which need to be verified, which should be compared with this, like which we did actually, like this statement and the other statement. So basically this is not a distributive lattice. Is that okay?
Okay, ma'am.
Okay, great. Let's move to the next question. Which of the following is the canonical product decomposition of the interval 1, 7, 2, 3, 5, 4, 6, 8? And you have 1, 2, 7, 8, 1, 4, 5, 6. So these two elements are there. So this is your interval. Now in NC8, so NC8 is basically non-crossing. So non-crossing is what? You have 1, 2, 3, 4. For example, if you write it in a cycle, then you cannot do this. So this is if you have 1 3 related, 1 3 in the same part and 2 4 in the same part, that this is not a non-crossing. So this is a crossing part. So this is not a non-crossing element. So that means this implies This is not a non-crossing. This should not come in. This does not belong to non-crossing 4. Okay. Now let's see what do we have. You have 1, 7, 2, 3, 5, 4, 6, 8. So let's see. These are two elements which are definitely non-crossing, because you have been asked in non-crossing NC8, what is this interval? Okay, how can you write it in the product form? So if you check the lectures, it will be clear anyway. But let's see. So you know that in the interval, in the normal thing, in pi 8, what should it be? So you have 1, 2, 7, 8. Here you have 1, 7 and 2 and 8. So you have these three part, 1, 7, 2, 8. And on the this above line you have 1, 7, 1, 1, 2, 7, 8, and you have 1, 7, 2, 8. So what are all the options you can have at this stage? So you have 1, 2, 7, 8. Here you will have 1, 8, 2, 7. Sorry, 1, 7 should be in the same part, right? So you have 1, 7, 8, 2, or you can have 1, 7, 2, 8, right? Is that okay? These
Okay, ma'am.
in pi 8, this is a situation of pi 8, because you remember when you have this 3, 5, 4, 6, 8, then you will just check in how many parts a number has been refined. Okay,
Pi 2
uh,
cross pi 2.
which one? Pi
Pi 2 cross 2 2 2 cross pi 2. 3
with
3 3,
3
sorry.
3, yeah, pi 3 cross pi 3,
1
right?
2 3. Pi
Because
3
in,
cross pi 3.
yeah, exactly, very good. So you are in this scenario, this is a situation of pi 8, but you are in now in
Yes,
non-crossing
ma'am.
part. Now in non-crossing 8, you don't have crossing elements basically. So you check whether these elements are non-crossing or not. Otherwise you should be in the poset basically. So to be in the poset, if any of them is a crossing element, then we have to remove it. So you cannot go to like NC3 or NC2, whatever it is. So let's see. So you have 1, 2, 7, 8. Okay, so you have the numbers 1, 2, 3, 4, 5, 6, 7, 8. You have 1, 2, 7. So you have 1, 2, and 7. So this is your crossing, like these three are related. 8 is separated. So you are actually in the 4 situation basically. So you have 1, 2, 7, 8, uh, which is the part you need to concerned about. Okay, or okay, you
Yes,
can
ma'am.
keep it in the general also, that's okay. So that is okay. So 8 is 8, and 1, 2, 3 are not crossing. Okay, so 8 is separated, so there is no issue, and there is no line which is crossing in this situation. So let's see what is the other thing. So for 178, so 178 is just this, and 2 is separated. So again there is no crossing. Okay, I'm just looking for those 4 because I can think of it in the product form, and I'm just looking for the pi 3, first pi 3. Now what about the third part? Third part is 781. Third is 1728. So you have,
1728. It's
yeah,
crossing.
yeah, that's a crossing. So there is an issue. So you cannot have this element. So you just have these 4 elements uh, in this situation with the first pi 3. So basically the point is now so with this 1728 wala part, so let's write it 1728. If I just write like this, for the time being, I'm not looking at other things. One 7 2, this is not actually right, but if I want to write it in NC, in NC let's say 4. So you have so you are comparing it with some NC non crossing thing, maybe 4, maybe 3, maybe 2, I don't know exactly. So we are, for example, let's see if that is same as NC3 or not. So for NC3 you have 1 2, so you have 1 2 sorry, 1, 2 and 3. So whatever you have, you cannot cross. In 3 you cannot cross. So for crossing there should be 4 elements basically. For crossing there should be something like cross. So that for that you should have 4 elements to begin with. So in NC3 all are, this is same as pi 3 basically. All the elements are non crossing. So but in this situation you cannot compare it with pi 3 because one element is gone, right? So in the
Okay.
1 to 7 8 part one element is gone, so you cannot compare it with the pi 3 thing. So and so this is one thing, you cannot write it as NC3. What could be the other possibility? Other possibility is actually this NC2 cross NC2. What does that mean? You have 1 2 and you have one this partition, so you have just one line and the other line is for example 3 4 3 4, or maybe you if you want to write, or maybe let's write like this. So there are just two lines going up. So you have so there is this line and there is this line. So I'll write it. So you have this line and this line. So this is actually same as NC2 cross NC2. That is the thing it is saying. Okay, exactly what cross means. Cross is something. Cross is like dedicated 1 2. You have 1 2 and there is another 1 2 if you want to write like this. So there is comma. Comma means in the cross you have all the subsets basically, all the ordered pairs. So you have 1 2 1 2, there is one possibility. You have 1 2 1 partition 2, you have 1 partition 2 1 2, and you have 1 1 2 and 1 2. So these four elements are there in this situation, and if you want to connect it, and here you will have 1 2 1 2, okay, and you have 1 2 comma 1 2, and you have 1 2 comma 1 2. NC2 is again non-crossing thing, so all pi 2 is non-crossing because you need four elements to cross basically. So this is the situation, right? And that is exactly you have in your hand, this part. So this is same as NC2 cross NC2. Similarly, you can do it for 3, 4, 5, 6. This is exactly again NC2 cross NC2 because you will have 3, 5, and here you have 5 and 6. 3, sorry, this 3, 5, 4, 6. Again, you will have the problem with 3, 5, and 4, 6 because it will cross. 3, 5 is this, 4 and 6 is this. So it will cross. So again you will have this, you have to remove this partition. Okay, is that okay? So that will be your answer,
Yes,
NC2
ma'am.
cross NC2 cross NC2 cross NC2. Okay, very good. So yeah, now this is the question for this canonical product decomposition. Now calculate the Mobius function that you can actually do. Use the Catalan number formula, like that is just use the formula and
Minus
you can
1
do that.
whole power n
Yeah,
minus
yeah,
1, n
exactly,
minus 1
something
whole
like,
factorial.
yeah, this Catalan number of, I guess, n minus 1, and you can calculate this.
N minus 1 factorial.
Oh
N
there
minus 1 factorial.
oh there is no, that is different. That is mu of pi, but this is NC, this
Okay,
is
ma'am.
non-crossing. So that was the
Okay,
pi
ma'am.
12 thing, but for this is a Catalan number. So you can check the notes,
Okay,
I
ma'am.
can show you if you want. This should be like this. Yeah, Mobius function of not this, this is ideal, this one. So yeah,
Yes, ma'am.
this one. So it says mu of this is minus 1 raised to power n minus 1 cn minus 1. Just firstly you can again write it in the form of pi's, and then you have the 0 1 thing, the least, and least element the greatest element, and you can do that. Just use this and use the formula and you will be done. Okay.
Okay.
Yeah, just the calculation. There's a correction here because it is written 5 and 5. So you can actually do it on your own because number cannot be repeated. So you have 5 commas 5 and 6. Okay? Yeah.
Okay.
Okay, great. Okay. This one is an integer partition is a sequence lambda. So that has been explained in the notes also in for the week 2. So this is a weekly decreasing positive integer sequence. So you have something like, so this is a poset of all the sequences lambda 1 to lambda l, and l is not fixed, l could be variant. So and there's a decreasing sequence in this situation, and n is equal to, if n is equal to lambda 1 to lambda l, then we call it we say it lambda is a partition of n. So if you, so for example n is 4, and if you have 2 1 comma 1, then this is a partition of n. So lambda denotes a partition of n. So now, and this again a correction, set lambda I is equal to 0, is just greater than, doesn't make sense. So for so this is a sequence is usually of infinite length, so it is not like something tuple. So sequence is always infinite, so it's like if you are saying this is a sequence, you can actually assume the other elements to be 0. After l, this is just 0, so you can think of it as a sequence. Let Y be a set of all partitions partially ordered by lambda greater than, so the set of partitions. So basically you collect all the lambdas of such kind, you take this set, okay, you take this set, and two elements are related by lambda is greater than or equal to mu if for if you take mu I for all. So for example, let's say lambda has length l and mu has length for example m, and so for if m is greater than or equal to l, then you can do lambda I is greater than or equal to for all I in between 1 to l. So after that it is anyway 0. What have I said? I should not write like this. It should be L. So L is bigger, okay? That's why I'm saying this is bigger one, okay? So bigger one has to have the bigger or equal length, okay? If L is L, I'm using L to denote that, okay? And because after that this is just 0. So if you are comparing, then 0 is always on the lesser side, okay? So L is bigger if L is greater than or equal to m, and Li lambda I is greater than or equal to mu I for all I 1 to m, then this is done, okay? So then lambda will be greater than or equal to mu. That is the rule. Now if you have given lambda to be 5542 and mu to be 432, that what can you say by lambda mu? That is the question. So what can you say about meet of lambda and mu? Okay. So again, again this will be what? This will be the least element of the set. All those x, or maybe if you are writing t belongs to p. So this is your the set. T belongs to p such that again you sorry, I should write greatest because you are talking about meet, so it should be greatest, such that t is less than or equal to lambda and t is less than or equal to mu. Okay, this is your thing. So greatest element of this set. Now what are all the t's can come here which are less than lambda and less than mu? So it should have the value as value, it should be less, right? So just pick the lesser values. So lambda what is this, meet, lambda meet mu will be what? So you take the lesser values, so 4, Here at the second place, what do you have? 3 and 5. You take 3.
3.
For this you take 2, and the next one is like 0,
2.
so you are taking 0. So basically 0 we don't write, so you can write 4 3 2. After that, this is just, these are all 0, right? So
Yes, ma'am.
this will be your greatest element of this set, because you are talking about the,
Greatest element.
yeah, the lower elements. So this will be just 4 3 2, and you pick the greatest one. So you are not taking 3 because 4 exists, and that is all also less than lambda and mu. So that will work. Similarly, for the same question, if you have lambda to be 3 comma 1 and mu to be 2 comma 2, then lambda join mu should be what? Lambda join mu will be
Least element of the set.
yeah,
Least element of the set.
least element of the set. This t belongs to p such
T
that
belong.
now t is on the bigger side, this one, and you have mu less than or equal to t. Okay.
So,
Now, yeah. Now you are talking about the bigger one. So you consider the bigger element here. So bigger element, now you take 3 and 2. Bigger one is 3.
3.
And you have
And
other
2.
one is 2. Yeah, bigger is 2.
2.
So this should be the join, because this element is bigger than both of these elements, and there is nothing in between also. Nothing can come in between, because 3 is already biggest. Like, you just take the maximum value basically. So this is your yeah, 3 comma 2 is your greatest, yeah, the join of lambda and mu. Okay, very good. Now, okay, for dn, now dn, you know, remember divisibility thing. So for d69 you have 3 join 23. So as I said earlier, it's like GCD you are calculating. So you are saying there is 3, there is 23. What is coming lower than that? That is going to be 1, because these are prime numbers, right? 3 and 23 are prime numbers. So when you make the divisibility thing, the Hesse diagram, you will have 1 at this position, right? Because there is nothing in between 3 and 1, there is nothing in between 23 and 1. So the number you will get just 1 only. So the joint, sorry, the meat will be this. So you can actually say this is GCD.
Greatest.
Yeah, greatest common divisor. Yeah. Okay. Let's move to the next question.
Equal to 1.
Yeah, equal to 1. Okay, yeah, this is an interesting question. So this was, I was saying earlier. So lattice. So for, is this a lattice or not? So this is a very good example where the set is so you are checking about all, for all x y belongs to P, whether x join y and x meet so x join y, x meet y exist or not. That is the question. Exists or
Exists.
not? Okay, that is the question. Okay, let's check it. Okay. Now the point is, earlier what is happening, for example, when you are talking about 1 2 3 and 1 3 2, and if I don't consider 1 2 3, then the join will not be some anything, like there does not exist any element which is above that, right? So that does not exist because the set is itself empty. Okay. Now here things are going little bit weird in the sense that if you consider, so I'm giving you the answer. So if you consider these two elements b and f, you consider b and f, now try to calculate what is the join. Okay. So for b and f, so all those elements, so you are again considering least least element of the set T belongs to P such that B is less than or equal to T and F is less than or equal to T. That is the thing, right? Now, what are all the elements which satisfy these properties? Let's see what is this set. Can you tell me one element at least in this set? So above B and F you are looking the elements. So above B and F. tell me at least one element which will.
C.
Sorry, which one?
C, ma'am.
C. Okay.
No,
S-
D.
yeah, B is related to C, but there is no connection between C and F.
No
And there,
connection with F.
yeah, so T
C.
should be bigger than F. So there should be a relation. So you check. So C is
And
not
F
there.
also we can't say G.
Yeah, G is again you cannot
D.
take. Yeah, again, exactly. You take D because there is a relation between both of these. So I can change color. So you
Mm.
there is this relation, this relation. Both are related, and D is on the bigger side. So
D and H.
yeah,
H.
H is there. E is also there because E is biggest, so you can always have
Yes,
it.
ma'am.
Okay, so you have these three elements. Now you are checking for the least element of this set. Can you have such
Mm.
element?
No, ma'am.
Hmm.
Does not exist.
Yeah, exactly. So there is just this relation. D and H are not are incomparable. So you cannot have anything on the
Mm.
lower side. So this does not exist. So this is a very good example to actually this is kind of non-trivial example. And such
Mm.
examples exist in divisibility. If you can try with divisibility, you can have the prime numbers, then you can always have, for example, you can take I don't know, 2 6 1, and let's say this. Oh, not this. You can take the bigger one. Okay, you try with something, I'm not sure, maybe 18. Try with that. Or maybe last time we took 54, it was something like this, the diagram was something like this, and then check whether this is a lattice or not. So divisibility uh, many of the times fails in terms of lattice. Not every, but many of the times. Okay, whenever you have some different prime factors, so like 54 has 3 and 2 as prime factors, like two of the prime factors are these. So there it will happen. Okay, great. Okay, 17 question you can try. Actually, this is something exclusion principle. Okay, this is
Okay.
exclusion formula. If you didn't if you have doubt, I can explain it next time. I'm not so it might take time a bit. Okay, you can try this
Okay, ma'am.
exclusion formula, and you can check what is the answer and these things. I can explain it next time if you need. Okay.
Okay, ma'am.
Okay, so week 2 is done. So I'll just explain, if possible, two questions of week 3. Okay, so that like whatever I said in the beginning, I can do that at least. Okay, so
Okay.
consider the ring of formal power series. So if you see what are formal power series, the collection of like a n x raised to power n
And
is equal to 0 to infinity. You take
0 to
such,
infinity.
yeah, such kind of elements you take, and an's are an belongs to the field f. Okay, you take this is the set of formal power series. This is said to be a formal power series, so we are not saying they should converge. So this is just a written expression of something, like we are not saying they should converge at some point. For example, in Cauchy sequence and these things, you always think of like, will it converge? In polynomial set will converge because after a point it is ans are going to be 0. But this is just a notational purpose. Okay, so this is a ring of, consider this ring of formal power series, and we denote it by this double brackets. This is a very interesting ring actually. Then for any f, the multiplicative, you need to find what is the multiplicative inverse of this element. Okay, you have 1 plus 2 square x plus 3 square x square plus 4 square x square x cube. So you have such element, let's say this is f. So there's a trick to do that. This is the general trick we used to do in like high school. So
N square.
yeah, sorry, yeah. So
Nothing, ma'am. Nothing, ma'am.
yeah, an is like x n square here. So
N x square.
yeah, so multiply by x, you will get x plus 2 square x square plus 3 square x square plus 4 square, sorry, cube, and here x raised to power 4 plus up to and so on. Now you subtract it, okay? You will get, sorry, not f. So this was the trick. I think I at least used to do that in 11th 12th. So it's like 1 minus, you subtract it, what will you get? 3x. So it's like n square minus n minus 1 square. Okay, you are subtracting because you will subtract the coefficient of x. So it's like this, what will you get? N minus 1, and on the other side you will get this, sorry, minus 1. So this will be just 1, and here you will get 2n minus 1. Okay, so you can actually generalize this and write it. So it's like n is equal to 2, so you will get 3. So it's like the odd numbers you will get. So you will get plus 3x, because 2 square minus 1, 3 square minus 2 square, you will get 5 from this thing, and continue like. So you will get all the odd numbers. Okay, 7x cube. Okay, now what I'm trying to do, basically, if you see in the lectures, there's a so you know, so you are trying to write f in, you are trying to find the multiplicative inverse. So basically, if you check the notes, the multiplicative inverse will only exist if the constant term is non-zero. That is a theorem, you can check that in the notes itself. So if this constant term is non-zero, then you will search for the multiplicative inverse, basically. So there exists a multiplicative inverse. And other thing is, if you have 1 plus x plus up to and so on x square, uh, I should not use sum, or I can write this, or maybe you can write 1 plus x square. So the inverse of this element, or not inverse, this value is actually 1 by 1 minus x. So what I mean to say, this is inverse of, not n, this is the inverse of 1 minus x. So that again you can check. So there is, these two elements are inverses to each other in this formal power series situation. Okay, you usually, when you have seen this uh, like 1 plus x square, or like in the geometric progression thing, so you have 1 by a minus 1, a by 1 minus r thing, where you used to say that x is like x, or maybe 1 plus r square, where r is less than or equal, not equal to, less than 1. Then you can say that the sum is a by 1 minus r. That used to happen, right? Not used to, like you
Okay.
used to do that. So in geometric progression, if you remember, 1 plus r square, like not geometric, so this is a geometric progression. So you got the sum to be this whenever mod of r is less than 1. But here there is no condition on x is just a variable. So that's why I'm saying this is a formal sum. We are not saying this should converge or somewhere. Okay, so what I'm trying to do, trying to get this kind of element to be in terms of 1 plus x square kind of thing. Okay, I'm trying to get this value. Okay, so that is the task, because I know the inverse of this element is 1 minus x. So if I can write it in terms of in terms of this element, then I know the inverse of this element, 1 plus x square up to and so on, is 1 minus x, and I'll use it. Okay, so let's do that. 1 minus x f is equal to, you got this. Now again you have this odd thing. Now to remove these elements, what you can do, again you can multiply by x. Then, so let's say this is your g, so you can write it g. So for simplicity, now multiply by x. you will get 1 you'll get x plus 3x square plus 5x cube. Okay, now you subtract this. So when you subtract, 1 will stay like this. Now you have this. So 3x minus x is 2x. 5x square minus 3x square is 2x square. Similarly, you will have 7x cube, that will be subtracted by 5x square. You will get 2x. Now you will just get 2, 2, 2 only. So this is like you can take 2 to be common, and you will get, and you can again take x to be common, and you will get this 1 plus x square plus up to and so on. So that was exactly I was doing. You can write 1 minus x into g. This is 1 plus 2x. Now this element, you know what is the inverse of this element. Also I can, now what is g? This is this 1 minus x, and g, this is 1 plus 2x, 1 plus x square plus up to and so on. So you can actually write it, sorry, not g, this is f. This sorry, this was the value I am using. So this is like 1 minus x square f 1 plus 2x, and you can use 1 minus x here, because 1 plus x square, because these are inverses to each other, so I can write 1 by 1 minus x, and f will be like 1 minus x plus 2x by 1 minus x, and there will be q, just the calculation. So x should be like this, f should be like this. Okay, now so in terms of, so if you need f inverse, it's like you are doing this. Oh, so actually you will get 1 minus x cube, and the multiplication with 1 now. Okay, so this is something, okay, minus x plus x square minus x cube. You can actually check that, because if 1 minus x is this, so you can put at the place of x to be minus x, and you can get this. So I'm just inverting this element 1 plus x. So this multiplication should be your inverse. Is that okay? I went little bit
Yes, ma'am.
fast, but yeah, I hope this is clear.